start with a short presentation of myself. I did a PhD in inorganic chemistry more than 20 years ago in Germany, did a postdoctoral fellowship in France, and I'm working at LINSEIS company in sales and application support since almost 10 years. I speak not only English, but French, and as a mother language, German. So if you feel more comfortable in writing English or French or German in the chat, or later on an email to me, you can do it as well in German and in French, not only in English. Okay, so let's start about the thin film analyzer. The thin film analyzer, manufactured by LINSEIS, is a platform for the measurement of thermophysical properties of thin films. So a short agenda. I will start with a short company presentation, do a short introduction to thermoelectrics. Why will I talk about thermoelectrics? This is due to the fact that the thin film analyzer was initially developed for the analysis of thermoelectric materials, but you can obviously analyze any type of thin film, not only thermoelectric materials. I will continue with showing you the LINSEIS product for thermoelectric applications, and then show the thin film analyzer, its concept, the setup, and some applications. So the company LINSEIS was founded in 1956 by Maximilian LINSEIS, whom you can see on this picture. The actual CEO is his son, Klaus LINSEIS. Actual managing director is the son of Klaus, grandson of Maximilian. And the head of R&D is a brother, Vincent LINSEIS, a brother of Florian LINSEIS. So it's a family-owned company in the third generation. Our production plant, development center, application lab, and so on are all situated in a small town in the southeast part of Germany, in the region called Bavaria, where we do the manufacturing. We have own sales and service locations in further countries, in the United States of America, in India, and in China. And we are represented by distributors worldwide. So we started in the 50s producing mainly dilatometers. And to do the data acquisition, we built data logger and flatbed recorders. So those are nowadays replaced by computer acquisition, obviously. But we built them till a couple of years ago. In our factory in Germany, we also have some application laboratories to run customer sample and test the performances and suitability of our devices concerning certain analyzers to be run. Our product range comprises different types of equipment. For example, calorimeters for the measurement of chemical reactions and phase transitions. Thermobalances for the measurement of mainly chemical reactions, weight changes. There are devices called simultaneous thermal analyzers, which are combinations of a thermobalance with a calorimeter. So allowing to measure these two parameters in one sample run. Furthermore, we build devices for the measurement of dimensional changes, so dilatometers and thermomechanical analyzers. We do have a very broad range of instruments for the measurement of thermal conductivity and thermal diffusivity. Some analyzers for the characterization of thermoelectric materials in general, and some instruments for the measurement of thin films. One instrument is dedicated, or one series of instruments is dedicated for the measurement of semiconductors and to measure the Hall effect. In general, our instruments can be fitted with evolved gas analyzers, so spectrometers, in order to characterize outgassing materials out of the sample. And we do a lot of customization, for example, to build instruments working at high pressure. mainly for calorimetry and thermogravimetry. So let's have a very brief look on what is thermoelectricity for those who are not familiar with this topic and but are interested in it. We do dedicated webinars for the basics of thermoelectricity from time to time. So have a look on our website to find such webinars. So what is thermoelectricity? Thermoelectricity describes the direct conversion of a temperature gradient into electricity or vice versa. So the most known effect, probably everybody of you will know it, is a Peltier effect. The Peltier effect describes when you power it up, such a Peltier element, when you power it up, it will separate cold and hot. So this is the effect used in such cooling boxes to generate cold. The inverse effect is a so-called Seabeck effect, which describes how electricity is generated from temperature gradient. These topics are important and interesting, for example, for waste heat recovery. For example, in exhaustion pipes from cars, there is a hot part, the surrounding air is quite cold, so you get a temperature gradient. And if you manage to harvest a voltage out of this temperature gradient by a thermoelectric material, by the Seabeck effect, you get power for free. Other applications for thermoelectricity are autonomous power sources and sensor materials. So let's have a little closer look on the Seabeck effect and what it is. So you have a thermoelectric material. If you heat it up on one side and cool it down on the other, you will get a voltage as a response to this temperature gradient. And dividing the harvested voltage by the generating temperature difference, you get a value which is called the Seebeck coefficient. And this coefficient is very important to characterize thermoelectric materials. In order to characterize thermoelectric materials even better, there is something called the figure of merit. A figure of merit in general is a quantity which is used to characterize the performance of a material, device, a system, or a method relative to alternatives. So it allows to compare the performance and the utility of a material or device for a certain application. The figure of merit for thermoelectric material is defined by this formula. Zt, the figure of merit, equals the Seebeck coefficient squared, multiplied with the electric conductivity, divided by thermal conductivity, multiplied with the temperature. Often, thermal conductivity is not measured directly, but by a method called the laser flash method. And the laser flash method gives, first of all, the thermal diffusivity alpha. And you have to know and to measure the heat capacity and the density in order to calculate the thermal conductivity. So there are quite a lot of measurements to be performed to get the figure of merit. And the aim is in thermoelectric research is to maximize the figure of merit. And this can be done by increasing the Seebeck coefficient, increasing the electrical conductivity, or by decreasing the thermal conductivity. So all these parameters have to be analyzed. There is an alternative method, the so-called Harman method, which allows the direct ZT determination in one measurement. But this does not work for thin films and can only be with different machines. So once you got your thermoelectric material, you can start to build so-called thermoelectric generators, which will produce significant power output. And LINSEIS manufactures different devices for the characterization as well as from the legs as for the thermoelectric generators. The analysis can be done on bulk materials, on thin films, or at very low temperatures or very high temperatures, up to 1,500 degrees. But let's focus on the thin film analyzer, which is the topic of today's webinar. So, first of all, why should we be interested in measuring the thermophysical properties of thin films? Why don't we just take literature values or just measure bulk materials? This is due to the fact that the properties of thin films, the thermophysical properties of thin films, depend on the size, and they are different of the properties of the bulk materials. And this is due to surface effects, due to different aspect ratio. You have much bigger surface compared to the volume for thin film than for bulk material. There is also an influence of surface scattering and boundary scattering. And all this influences the properties of the thin film compared to the bulk material. On the right-hand side, you see an example. We show the thermal conductivity as a function of temperature. In this case, for silicon nanowires, so for one-dimensional objects. And depending on the diameter of these nanowires, the thermal conductivity changes dramatically. For very thin layers, thin wires, it's lower than 10 watt per meter Kelvin. For thicker wires, it goes up to 50 watt per meter Kelvin. So you really have to measure the thermophysical properties of the thin film, and you can't just take the values from the bulk material. So the LINSEIS thin film analyzer, TFA, is a modular hardware. The basic configuration, which you can see here on the left-hand upper side, is a configuration allowing to measure the thermal properties, thermal conductivity, and heat capacity. Then there are further add-ons. One add-on is the so-called Thermoelectrics add-on for the measurement of Seebeck coefficient and electric conductivity. There is a Hall add-on to measure the Hall constant. From the Hall constant, charge carrier concentration and mobility can be calculated. The Hall add-on can be either by a permanent magnet or by an electromagnet. The electromagnet version is shown on the right-hand side, and the permanent magnet version is shown here in the middle. The electromagnet version allows for sweeping the magnetic field just by changing the power supply of the current of the electromagnet. In the case of the permanent magnet, we have two magnets, in fact. One in the positive direction, one in the negative direction, and there is a zero position when the sample is outside of the magnetic field. So we have, in this case, plus field, negative field, and zero field. The measurement is based on disposable sensors, so-called chips. They are consumables, and all those parameters can be measured with one type of chip. And the thin films you can analyze should have a thickness of at least 5 nanometers. You will see the thickness you will need for analysis later on a further slide. So what is the concept of the measurement? The concept is to have these chips, so pre-structured measurement sensors. On these sensors, there are two zones. One zone with a so-called Joule heating method. This allows for the measurement of thermal conductivity and specific heat. And on the other side, we have a 4-point measurement setup for the electrical parameters, electrical conductivity, the Seebeck coefficient, and the Hall constant as well. On the other hand, you have your sample, and you have to bring your sample on this sensor, and you can do it by different sample deposition methods like sputtering, evaporation, printing, coating, and so on. And once you deposited your sample on the chip, you bring the chip to the instrument, to the measurement chamber of the instrument, and you perform your measurement. So this is a theory. Let's have a look how it looks like in real life. On this picture, you can see the disposable sensor compared to the smallest European coin, a 1-cent coin. So it's approximately 1 by 1 centimeter, this chip. On this chip are different zones, and this zone in the middle should be covered by the sample, and the other contact shouldn't be covered. So we need so-called shadow masks, which you can see here in this picture, to protect these regions from the sample and to deposit the sample only in the center of the chip where it should be. We have different types of sample masks, of shadow masks, metallic ones or polymer foils, and they have to be chosen according to the sample deposition method and temperature. So once you apply the shadow mask, you do the sample deposition by, in this case, by magneton sputtering, but the other methods are possible as well. And once the sample, the thin film is deposited on the chip, you remove the mask, get the sample on the chip, and you place the chip inside the machine and perform the measurement. So let's have a look on the instrument. This is a basic configuration, and underneath this lid, you will find this measurement chamber, which you can see on the right-hand side. This is a vacuum-tight measurement chamber. Vacuum is important for the measurement of thermal conductivity. There is a sample holder or the chip holder. This can be heated up to 280 degrees centigrade to perform measurements, not only at low room temperature, but also at high temperature. There is a piping feeding liquid nitrogen. With this liquid nitrogen, you can cool down the sample down to minus 170 degrees. So you can perform also a measurement at low temperature. And then you put your chip with the sample inside this sample holder. And you fix this little lid with these 4 screws on top. You see the lid enlarged in this picture, and there are some pins, spring-loaded pins, which will do the contact to the chip and to the sample. So it's very easy to perform a measurement. You just have to fix the lid. There is no further bonding or soldering or delicate procedure necessary to do the contacts between the machine and the sample chip. And then, once you placed all inside this machine, you fix again this lid and start your measurement. So the thin film analyzer has some advantages. It allows for automatic measurements at different temperatures, for example, with an easy data evaluation. Sample preparation is fast and easy, and you can analyze a lot of different types of materials, like inorganic materials, organic materials, metals, and so on, in a temperature, in a thickness range of a couple of nanometers up to some tens of micrometers thickness. Sample preparation can be done by various methods like physical vapor deposition, chemical vapor deposition, coating, spin coating, drop casting, and so on. All measurements of all parameters are taken in the same direction, in the plane of the thin film. And this is very important because we saw on a previous slide that thin films are highly anisotropic, and you should measure all the properties in the same direction. And as all measurements are taken on the same sample deposited on the chip. You avoid errors due to different sample compositions or sample geometries, or due to different environmental conditions like different heat profiles. So you can really compare all the results to each other because they are measured on the same sample under the same conditions. So let's have a look how thermal conductivity is measured. It's a hot stripe method, which I will show. It's implemented in this small brown region. It's a very tiny membrane. If we cut the chip and have a look on this side of this membrane, we see what is depicted here. So there are rims made from silicon. On top is a very tiny membrane of 100 nanometer thickness. There is a hot wire implemented. A passivation layer is coating this membrane and the hot wire. And on top, the sample was deposited. There is an alternative deposition method, which is used in quite few cases. If the deposition is not possible from the upper side, you can do it as well from the lower side of the sample, of the chip. We use a so-called 3 omega measurement technique, which means that we feed an alternating current through this hot wire, and we measure also the temperature change during time with this hot wire. So this hot wire will generate a heat flux through the sample, but also through the membrane. So in order to get the heat flux only from the sample, we have to do an empty chip measurement to know the influence of the empty chip and to eliminate it from the sample measurement and to get the results from the sample only. So, an often asked question is, what are the sample thicknesses I can analyze? So, if we consider that the effect of the sample should be at least as big as the effect of the empty chip, we can do a calculation, which is shown, and the results are shown in this table. For highly conducting materials like metals, having a thermal conductivity in a range of 100 watt per meter Kelvin, we need film thicknesses in a range of a couple of nanometers to a fraction of a micrometer. For typical thermoelectric materials with medium thermal conductivity in the range of a watt per meter Kelvin, we need some tens of nanometer thickness up to approximately 1 micrometer thickness. Organic materials like this thermoelectric material P.PSS, having low thermal conductivities, the thicknesses have to be even higher in the range of hundreds of nanometer up to 10 or 20 micrometer. The thicknesses have to be known in order to calculate the thermal conductivity. So we have to measure the thin film thickness. This can't be done by the thin film analyzer, but you have to do it by alternative methods. So this was how to measure, thermal conductivity must be measured under vacuum, because otherwise you will get also a heat flux by the surrounding air. Seebeck coefficient can be measured also by in a gas atmosphere, but is normally measured in the same one as thermal conductivity under vacuum. So this big brown membrane here is, which you can see enlarged on these two pictures, is used to measure the Seabeck coefficient. As you can see here, there is also a hot wire implemented in this membrane, and this serves to heat up the material and to create a temperature gradient. The temperature on the hot side of the sample is measured by the resistance thermometer here, very close to the heating wire. The temperature on the cold side is measured in the middle of the chip. And there is a contact here, an electrical contact to get the potential on the hot side of the sample. And we use this pin, this cold contact, to get the voltage over at the cold side. So we measure the voltage between this cold place of the sample and this hot contact, and dividing it by the temperature gradient between these two places, here and here, we get the Seebeck coefficient. The temperature gradient can be adjusted by the current you feed in this hot wire. Electrical conductivity is measured by the well-known and well-established van der Pauw method. The van der Pauw method needs a homogeneous layer thickness. Once again, this layer thickness has to be measured by an alternative method. It can't be measured by the thin film analyzer. For the van der Pauw method, you also need contacts which are small compared to the sample and which are at the edges of the sample. So this can be seen on this picture. These four contacts have to be small and on the edges of the sample. And this is fulfilled by using the sample deposition mask we saw in the previous slide. And then you perform measurements of the resistivities between these 4 points. And you apply this van der Pauw formula and you get the electric resistivity. The Hall constant is measured in the same setup. You just apply a magnetic field perpendicular to the sample surface. This can be done by one of the Hall add-ons, the electromagnet or the permanent magnet. And once more, you measure the resistances between these 4 points with a magnetic field and without a magnetic field. You apply this formula and you get the Hall constant out of the resistances between these 4 points. You have to know the magnetic field and once more the sample thickness. So this means you need a sample thickness for the thermal conductivity measurement, for the electric conductivity measurement, and for the Hall constant. It's not necessary to know the thickness for the Seebeck coefficient measurement. So this was a hardware part of the machine. There is a software part as well. The software consists of different modules. There is this measurement software, which allow to do temperature and magnetic field swipes. So the electronics will do the measurements by the basic device and the add-ons. You can set up the heating profiles and measurement tasks. You can see the current values from the sensor and the sample's raw data, and you can do regulations. Once the measurement is done, you go to the evaluation software, and in the evaluation software, you have integrated plugins to do very easily the evaluation of the raw data. For example, for the thermal conductivity, you can do easily the zero curve correction and the calculation of the specific heat. You can calculate also, do the evaluation of the other parameters, Seebeck coefficient, resistivity, Hall coefficient, and so on. And you can calculate the power factor and the figure of merit. All the data can be plotted against time or against temperature, and you can export the data in ASCII format. So let's have a look on 3 applications. On the upper picture, you see the analysis done on thermoelectric film made from bismuth antimonide. The film with a thickness of 84 nanometers was prepared by thermal evaporation. And what you can see is in pink, the thermal conductivity over temperature. Blue is the electric conductivity. Green is Seebeck coefficient. And from these values, the figure of merit is calculated and shown here in yellow color. The lower picture shows the result for thermoelectric polymer film, organic material with a low thermal conductivity, P.PSS. The film was prepared by drop casting method. And as we saw previously, for materials with low thermal conductivity, you need thicker samples. In this case, the film had a thickness of 15 micrometer. Once more, you find thermal conductivity over temperature. You find electrical conductivity, the Seebeck coefficient, and from these parameters, you can calculate the figure of merit, shown in yellow. The last example shows the measurement of a metal, of gold. The film was prepared by magnetron sputtering, had a thickness of 100 nanometer. Gold is poor thermoelectric material. It has a large thermal conductivity and a low Seebeck coefficient. Again, the results are shown in pink, thermal conductivity, in blue, electric conductivity, in green, the Seebeck coefficient, and in yellow, the figure of merit. For those who are familiar with thermal conductivity of gold, the literature value for bulk material is approximately 300 watt per meter Kelvin. And for this thin film, we find only half of the value of the bulk material, approximately 150 watt per meter Kelvin. This shows that it's really necessary to measure the properties of the thin film and not to take just literature values from bulk material. This is not a measurement error, but real life. We checked it by the so-called Wiedemann-Franz law, which holds for metals. It says dividing thermal conductivity by electric conductivity will give a constant value, the so-called Lorentz number. And this is the Lorentz number calculated from these results are in a very good result agreement with the literature value. So let's summarize. I showed the thin film analyzer, which is an instrument for the measurement of thermophysical properties of thin films. Thin films can be have thickness in the range of nanometers to micrometers. The thin film analyzer is a modular system with a basic instrument for the thermal parameters, conductivity and heat capacity. And there are add-ons, an add-on for thermoelectrics, for the electric resistivity and the Seebeck coefficient. There is a Hall add-on to measure the Hall constant and to calculate charge carrier concentration mobility from this Hall constant. Measurements are usually performed under vacuum. This is absolutely necessary for the thermal conductivity, but usually also the other parameters are measured under vacuum as well. The instrument allows to run measurements from -170 up to 280 degrees in a magnetic field which can go up to 1 Tesla. And all measurements are performed with the help of disposable sensors, so-called chips. All these parameters are measured in the plane of the thin layer. And there is only one sensor type necessary to measure all these parameters. So you get all the results from one sample if your hardware is equipped for all these parameters. So I would like to thank you for your attention for this presentation.